Okay. Okay, well, thanks all for coming. It's a great pleasure to introduce our very special speaker today. But before I do, I just want to mention that this is being recorded, so any questions after the presentation, just wait for the mic. This is being, as I said, video recorded just of the presentation and the voiceover. And also, aspects of this lecture have been published, and we're going to put that on the Centre for Climate Science's website, so you'll have some sort of written document of, to a large extent, the lecture. There's probably some things in here that's not quite covered, but nevertheless. It's a very great pleasure to introduce Dame Julia Slingo, who's not only a colleague of mine, has been a colleague of mine for quite a long time, but she's also a kind of a dear friend. And so I've got a CV here, and I just don't quite know what to say. It's kind of hard to introduce her. She, as you probably, many of you know, she was until about 2 years ago, a year ago, 2 years ago, the chief scientist for the Met Office. She has all sorts of accolades, and while she was a chief scientist of the Met Office, she really was the sort of shaped the weather and climate sciences of the UK, was one of the most influential and designated one of the most influential scientists in the UK at that time. She has many sort of accolades. She's a foreign member of the National Academy of Engineering in the US. She's a fellow of the Royal Society. She has been awarded the OBE, and also, I have to read this because I just call her the Dame, but the Dame of the Order of the British Empire. She has more flipping letters of the alphabet attached to her name than there are letters of the alphabet. So I can't go through all of these. There's a British thing to do to have these letters attached to your name. She's also an has an honorary degree in 8 different universities. She's not going to quite catch Sir David Attenborough, who has 35 honorary degrees, but you know, it's a kind of a really impressive resume. She's also designated, and this is not just a term of endearment, she's also designated as a national treasure. She is a national treasure, but she's actually literally a national treasure. And so, you know, it's a great pleasure to introduce her. But before I bring her up, I also want to note a couple of special members in our audience too. The Consul General of the UK, Michael Howells, is in the front here. And the Deputy Consul General, Colette Weston, is also in the audience here. So when the national treasure comes to these foreign shores, they have to be in attendance, I guess. Okay, so it's really a great pleasure to introduce Julia. It's going to be a fascinating talk. I think we'll all enjoy it. And welcome.
Thank you very much, Graham. I'm not sure about the national treasure bit, but anyway. It's really good to be here, and although I'm retired, I'm not completely inactive. I do spend more time in the garden and sitting on the sofa than I used to, and singing in choirs. And for some reason, you probably can't. But I thought it would be really interesting to give you a sort of a sense of where climate science is, where it's come from actually, because sometimes we don't do that, and talk about 2 cutting-edge pieces of research that I initiated in my final year or so when I was chief scientist. So I want to talk about climate science and actually give you a sense of its fundamental role still in addressing 21st century challenges. It's very easy for us to say, if we're thinking of climate change, that we've got the answer and all we need to do now is to fund all the technologists and engineers to find all the solutions. Well, that's not true. There is a lot of fundamental climate science still to do, and we need to remember that. But let's start with sort of just saying, what is climate? Well, this is a quote not by Mark Twain, as is often assumed, but by a geography professor. Climate is what you expect, weather is what you get. And so when we think about climate, we have to actually think about the weather. And this has been really my theme all my time at the Met Office, where we did everything from hourly weather forecasting to long-term climate change, was that the fundamental science is the same. And actually, if we're going to talk about the climate, we have to talk about the weather, because the way we'll feel climate change is actually through extremes of weather. It won't be the 2 degrees C rise in global mean temperature for sure. So you'll see this theme running throughout the lecture. And climate science is about understanding the Earth's climate, of course, through a combination of theory, observations, and computational models. I'm going to tell you quite a bit about the theory and the long legacy of that theory. I'm going to talk not very much about observations at all, just touch on them, and then spend most of my time talking about climate models and weather models and how we can use them to address 21st century challenges. So we're going to have a bit of history, British history to some extent, but also American history, because I think there's quite a lot of us who work in climate or in related fields who probably don't know some of this stuff. And we're going to start with Halley, of Halleys Comet. And, you know, this was the age of polymaths. People dabbled in all sorts of things, and he dabbled in trying to understand the trade winds. And of course, the UK being a maritime nation, they knew they had sailed the world seas and they knew about the winds. And this is a very iconic picture that was published in 1686, showing the winds, the trade winds, the winds of the world. And where he's actually put these little dashes here is where the wind reverses with season. So this is the monsoon. They knew about the southwest monsoon and the northeast monsoon. And Halley pondered about, well, why do we have these trade winds that converge pretty much on the equator? And he argued that it had to be to do with the passage of the sun during the day. As it went round the equator, it warmed the air up as it passed, and that drew the air in behind it as the sun went past, and so you had easterly winds. And that was in 1686 in the Philtrans of the Royal Society. The Royal Society was founded in 1660, so this is one of its very early publications. And that's basically what they thought at that time, that it was just to do with the passage of the sun. You have to go forward then about another 50 years to 1735, and George Hadley, who actually postulated that it was more to do with the conservation of velocity, how the air as it moves from the tropics towards the equator, having a less velocity of diurnal rotation than parts of the Earth it arrives at, will have a relative motion contrary to that of the Earth in those parts. So he'd already worked out that it was to do with the fact that we live on a sphere and that velocity was conserved. And he also postulated that the air converges in the hot regions, the air rises and descends somewhere else, and hence the Hadley circulation. He actually wasn't a particularly eminent scientist, and I couldn't find a picture of him anywhere. You can find pictures of other Hadleys, but George was obviously, maybe this was his big work. But anyway, very, very interesting. But there we are in 1735. We've got at least the essence of the Hadley circulation. And then you have to go really quite a long way forward, another 100 years, to Coriolis, who talked about the movement of objects within a rotating frame of reference. And Coriolis didn't actually think about a rotating sphere, the planet. But of course, his ideas were pretty quickly taken up by an American, in this case, Ferrel, who worked out that because of the Coriolis force, that if a body is moving, if it's moving into the northern hemisphere, it's deflected to the right, and in the southern hemisphere to the left. And that actually really then did explain the trade winds, and indeed the mid-latitude westerlies, which were known then as the passage winds. So you had the trade winds were the easterlies and the passage winds were the westerlies. And he, of course, worked out that it was the absolute angular momentum and not the absolute velocity that explains the winds of the world. So Ferrel was pretty important in actually establishing that because we live on a rotating sphere, we're going to have easterlies and westerlies. Interesting, it was published in the Nashville Journal of Medicine and Surgery, which probably says there wasn't much in meteorology going on in the US at that time. Who knows? It's extraordinary, isn't it? And then we have to go forward to Rossby. So here we've got this, we've explained the trades and we've explained the jets. But actually it was Rossby, again, working in the US, Swedish scientists working in the US, who I think, of course, set the foundations of dynamical meteorology and oceanography. And he established the theory of planetary waves, what we call Rossby waves, as a result of the Earth's rotation and of the stratification of the atmosphere or the ocean. And these Rossby waves basically set the scale of the general circulation that we know today. So this is Rossby's original drawing of Rossby waves. And within those, you get wave breaking, you get the formation of lows and highs, sets the scale of our synoptic systems. This is actually a picture of the flow in the middle troposphere in the very cold spell in 2014. And basically what you're seeing here are these characteristic, in this case, quite well amplified Rossby waves here. So here we are, we're in the mid-20th century before we really have an understanding that it's the rotation rate of the planet and the stratification of the atmosphere that sets the scale of all our weather and hence sets the scale of the climate. And those Rossby waves are modified, of course, by the presence of mountains and of the ocean, the presence of the oceans versus the land, but fundamentally it's about Earth's rotation. So there are some big constraints on the nature of our weather and climate, some very fundamental properties of the planet. So that's where we are with dynamical meteorology. We go back into the 19th century, and there was another group of physicists in this case who were looking at other aspects of the planet, its energy balance. And here we've got John Tyndall, who was working on trying to understand, they were very puzzled as to why the Earth was so warm. Because if you do a straight energy balance for a black body, the Earth should be quite a lot colder than it is. And it was Tyndall really who was able to explain that the atmosphere, and particularly water vapor, is a very strong greenhouse gas, and that's trapping radiation. But he also showed that these gases were emitters as well as absorbers of radiation. And that's really important for understanding the energy balance of the planet. And here we are, 1861, round about the same time, I guess, as Ferrel, who was working on the trade winds and the mid-latitude westerlies. We have this paper on the absorption and radiation, we would say emission, of heat by gases and vapors, and on the physical connection of radiation, emission, absorption, and conduction. And we would call that transmission of radiation. Again, in the Royal Society. And this is Tyndall's experiments, a very well-known picture where he actually measured the infrared effects of various gases. So here we are in 1860, understanding that we have the sun's energy coming in, but that actually it's gases and vapors that actually trap the infrared radiation and keep the planet warm. And this idea was taken up actually by Arrhenius, who was a Nobel Prize-winning physicist from Norway, and actually in 1896 he made the first prediction of global warming, and then he published in his book on Worlds in the Making in 1908 this statement about understanding that the enormous combustion of coal was going to lead to an increase in the amount of carbon dioxide in the atmosphere. So the theory of anthropogenic global warming is not new. It's been known for a very long time. And he postulated that if you double the CO2 concentration, you're going to get a temperature rise of 4 degrees C, which is actually still within the IPCC range. It's at the upper end, but actually we might think that he may be actually not far off being right. But interestingly, Arrhenius then went on to say, by the influence of the increasing percentage of carbonic acid, CO2, in the atmosphere, we may hope to enjoy ages with more equable and better climates, especially as regards the colder regions of the Earth. Ages when the Earth will bring forth much more abundant crops than at present for the benefit of rapidly propagating mankind. So he had a very positive view of the effects of global warming from very much just a sort of, I think, a non-dynamical view of what the climate, how the climate system works. And you know, that pretty well, and of course at that stage, in the early part of the 20th century, people were much more concerned that we were going into another ice age than anything else. So this was probably seen as quite a good thing. So here we are, we've got the dynamical basis of the climate, we've got the energy basis of the climate. But of course, there's an interesting other little story that was going on in the British Empire, which we often don't hear about. And this is the story of the British in India. And this is Henry Blandford, who went to India as its first director of the Indian Met Department. And when he got to India, he thought, gosh, this is great. Here we have order and regularity of the climate as prominent in India's atmospheric phenomena as are caprice and uncertainty those of their European counterparts. What he was talking about was that when he looked at his anemometer, he could see the diurnal and semi-diurnal pressure waves, was pretty well all the pressure variation he got in India, whereas where we live in the UK, the pressure is going all over the place and the weather is constantly changing. And he thought that he'd found in India a special place where he could understand meteorology. And I won't read it all, but it's sort of sobering to think that when I was working in monsoons, on the Indian monsoon in the 1990s, we thought that actually the complexity of India's position with its relationship with the Indian Ocean, with the Himalayas, with all the other aspects of the circulation, that India was probably the most difficult place to understand the meteorology, rather than the easiest. Anyway, Blandford thought he'd got a great place where he could do something. But of course, he came very rapidly unstuck because we had the global famine, the Great Famine of 1876 to 78, where there was a massive failure of the monsoon rains. And here we see actually, again, the conjunction of politics and science, reminiscent of where we are today. Our science is very much in the political frame, and it was at the end of the 19th century, because Britain relied very heavily on India for its cotton and grain harvests. And Indian taxes and to pay the dividends to investors was depended entirely on the monsoon rains, which actually are mostly incredibly stable. So everything had been geared to the regular return of the monsoon rains, and India was a vitally important asset to the British Empire. So Blandford was told, you've got to sort this out. We can't have this anymore. We need to control famine through climate prediction. We need to know what the monsoon is going to do so that we can govern India more effectively. So Blandford then spent a lot of time thinking about, is it to do with Himalayan snow cover? They thought it was the 11-year solar cycle had something to do with it. In fact, later on, we know that this was one of the biggest El Niños ever observed, happened in these years, and El Niño leads very often to failure of the monsoon rains. But he didn't know any of that, although he did know that drought in India was also concurrent with drought in Australia. He had a friend, Todd, in Australia who told him that. And then we come to one of my great heroes, Sir Gilbert Walker, who turned up in India at the beginning of the 20th century, and he really got to grips with this and pioneered statistical climate forecasting, which was basically how we did climate predictions, seasonal forecasting, all the way through the first half of the 20th century, and indeed in India is still done in this way. He called it seasonal foreshadowing. He didn't call it forecasting. I think actually foreshadowing is rather a good word, because we never know quite what the seasonal forecast is really tells us. But he performed masses of statistical correlations. He had a huge number of staff doing all these, analysing all these data. And he said, I think that the relationships of world weather are so complex that our only chance of explaining them is to accumulate the facts empirically. And that's true until we come to the age of supercomputing, when we now have a different way of understanding things. So he discovered these various oscillations, but he also sort of set the idea that the climate of one region can be heavily influenced by the climate of another. So in other words, when you look in a region and at the variability of the climate in a region, you have to understand it within the global context of these oscillations, what we now call teleconnections. So this is the beginning of understanding climate variability. And of course, it all came together with Bjerknes in the 1960s, who had been working on El Nino in the ocean and realizing that El Nino was a coupled phenomenon, and that you had to have a change, and that it was linked to this thing called the Southern Oscillation, which Gilbert Walker had discovered, which was why India had drought when there's an El Nino. And the two things came together, and we got the phenomenon, the mode of climate variability that we call the El Nino Southern Oscillation. And actually, it was Bjerknes who realized that actually, when you perturb the ocean temperatures and the atmospheric circulation in these ways, you perturb the overturning cells across the tropics, which he named the Walker circulation. So the Hadley circulation is the north-south. The Walker circulation we think of as the east-west. And so this is really, then we really have this concept now of the ocean atmosphere system as being critical for understanding the climate. And then, of course, we come to CO2. And here is the latest curve going up to December this year. And this, of course, is Keeling's, known as the Keeling Curve from Mauna Loa. I joined the Met Office somewhere around about here, and writing the first radiation codes and cloud codes to go in our latest climate model. And I wrote a paper somewhere around about here, which was on cloud feedbacks and water vapor feedbacks on a doubled CO2 world in a very simple model. It was published in a book called Carbon Dioxide, Climate and Society. I thought this was a bit of fun, an intellectual exercise. I little knew that actually what we were observing, I think we used to use 320 as the number in our climate model then, that actually we would be way up here at 410 in my lifetime, and that this curve effectively represents one of the great challenges for society now. So this has been a huge story for climate science through the past 40 years. And critical to all of that, of course, has been the way in which we've observed the planet. When I started in the Met Office, we were just getting the first satellite images. I did all my early work plotting radio sond ascents and thinking we had very little understanding of the global planet, the global Earth system. Now, of course, we know a vast amount about it, and we're continually, as I say, actually giving the planet a health check. And of course, JPL, NASA have been heavily involved in quite a lot of this. So Earth observation has given us enormous insights, but actually I would argue that all observations do is tell you what is happening, and they don't necessarily tell you why it's happening. So the other big change, of course, has been the development of climate models, which is where I started my career, building the first climate models in the UK. And just because I think it's a general audience, I just want to say a little bit about what these things are, because not everybody understands them. They basically simulate the climate system and actually the weather based on some very fundamental laws of physics. And they help us to explain how the climate system works, why it's changing, and what our future climate might be like. So I often call this my laboratory. So as like any scientist, I want the best laboratory that I can get my fingers on. So I want the best model and I want the biggest supercomputer. Because actually the skill and the usefulness of climate models is heavily tied up with the increase in supercomputing power. And I was well known in the UK for going to meeting with funders and ministers and saying, I need more money for supercomputing. And I did manage to get 100 million out of the UK government while I was chief scientist for arguably what is still the biggest machine dedicated to weather and climate prediction. And so, you know, that's what you do. I want the best laboratory, because this is where we test ideas. So these things, basically what we do is we cut the world up, we cut the atmosphere and the oceans up into volumes. And typically in the horizontal, the grid squares have up to now been around 100 to, say, 50 kilometers. So quite coarse, and we have about 85 slices through the atmosphere. So you're producing hundreds of thousands of volumes, which you then describe with their physical properties and integrate those properties forward in time using some fundamental physics. They're big codes. The latest unified model code at the Met Office was about 2 million lines of code. And they need machines that are several petaflops to run, and they produce a vast amount of data. So, but actually what's behind them all? Well, you know, it's actually classical physics. So when you actually look at what we're doing within these models, we're actually back to Newton's second law of motion. We have to add in the Coriolis force, which makes it slightly more complicated because we're on a rotating sphere, but it's fundamentally force equals mass times acceleration. We have used, and not so much now, this concept of balance, hydrostatic balance. But fundamentally, at the growth scale, that describes why the pressure decreases with height. It's a balance between the vertical pressure gradient force and the pull of gravity. In very high resolution models now, we don't use that balance because in systems like hurricanes and thunderstorms, there isn't a balance instantaneously. They're very non-hydrostatic. Mass continuity, quite simply, what comes in at the bottom has to go up and come out at the top. Ideal gas equation, everybody knows that from basic physics. First law of thermodynamics, linking heating to changes in the wind. Now this is where Earth's climate, particularly in the troposphere, gets really interesting. Because the Earth's temperature is such that you can have water in solid, liquid, or vapor form. And when you change from one form to another, you release or take up latent heat. And so you can actually move heat around the system through moving water around the system and then changing its state. And this is, in fact, the latent heat release when clouds and rain form actually dominates the Earth's heat engine. So that's why and we'll see that in a minute, this is why understanding how the atmosphere and the Earth's climate works is so complicated, because we can carry water in three forms. And here's the Clausius-Clapeyron equation, which relates the amount of water that the air can hold depending on its temperature. And we often quote this equation to argue that as the world warms, there's more water vapor in the atmosphere, and therefore we can have more severe storms. And then some very fundamental things to do with radiation. The Planck and Stefan Boltzmann's laws that link thermal radiation emitted by a body to temperature, and Kirchhoff's laws. that link absorption and emission of radiation by atmospheric gases. That's basically what we're doing when we build a climate model. We're taking some very classical immutable laws of physics and coding them up to describe the evolution of the atmosphere and the oceans. And what you get out is something that looks like this. So this is a simulation done actually rather a long time ago now, and there are probably some better ones around, at 12-kilometre grid. So this was done on a very big machine, and it's a representation of the infrared temperature, the black body temperature of clouds and the surface. So the white clouds are high clouds. The black surface is looking down almost to the ocean. If you're very careful, you can see the sun come past. There it goes. And when the sun comes past, the clouds build up and then fade away. This is entirely simulated by the model from those equations. The only fundamental constraints on this are the rotation rate of the planet and the solar constant, how much solar energy enters the system. This model is generating the water vapor in the atmosphere through physics. And in this case, we would have given it the other greenhouse gases, but not water vapor. So it's actually working out its own energy balance. It can see the mountains and so forth. Now, if you're an aficionado of tropical convection, like I am, Graham is, you know that this is actually not very good. That these clouds are not quite right. The frontal systems in these latitudes are very beautifully described. They're part of the Rossby Waves that I talked about earlier. But the tropics is really quite difficult. And the reason is that when you build these models, and because of the computer power available to you, you have to make your grid boxes quite large. Otherwise, you just can't get the problem through the machine. And so over the years, we've spent most of our time trying to understand how to represent physics that goes on at scale smaller than the model grid, how to represent their bulk effects. And they're things like the boundary layer and turbulence, and mountains, atmospheric composition, smog, radiation, probably one of the more tractable problems that we can solve. But the bit that's really still a major challenge for us is all of this. What's happening to the water cycle? How does cumulus convection work? How do we represent it? How does precipitation form? How do clouds form in polluted and unpolluted atmospheres? And so we're still absolutely, we have so much to do, but we have actually, I think, some really interesting new breakthroughs. In the last decade, we've seen, I think, a new age coming for climate and weather science. From, first of all, advanced Earth observation. This is the A-train, but particularly what we call the active sensors in space that Graham's been very much involved with, have allowed us to look down into these clouds and see where the precipitation is formed, and to understand, in combination with other observation, what the processes are. They've actually transformed a lot of our thinking about how rain is produced, particularly in convective clouds. And then, of course, we've had this ability now to perform very high-resolution simulations. This is one we did a few years ago at the Met Office of Super Typhoon Meggie at 1.5-kilometre simulation. And what you can see here starts from a very smooth field, and the physics of the model generates all these interesting cloud structures just from the physics. This is actually a remarkable simulation of this particular event with the cloud bands and so forth. And if you put that along with this sort of information, you learn an awful lot of new things about how convection, latent heat release, interacts with the dynamics of the system to grow things like hurricanes and typhoons and so on. So this has been a huge breakthrough in the last decade. And I think the ability now to do what I call computational field experiments, to study in great detail this system, for example, which you could never do in real life. You couldn't go and look at the four-dimensional structure of a system like that in every bit of detail to understand what it's doing. You can with a simulation. So this is really, really exciting for our understanding of some of the fundamental physics that's going on. And of course, it's been for us in the Met Office, this became part of our operational system while I was chief scientist. It was a major revolution in weather forecasting. This is an example of a forecast way back in 2012. This is the radar image here, and this is the model forecast. And this was actually a red alert in the UK for heavy rain through just where I live, which is about here. And I was actually due to go to a garden party at the Vice-Chancellor's house at Exeter University, and needless to say, I stayed at home. I couldn't have got out of the town if I'd wanted to. This was very typical of the quality of forecasts, and these colours are the hourly rain rates. So it gives now a very, very good sense of the flood risk and surface water flooding. And it's just been an amazing advance. And we've used the same models now to look at local climate change scenarios and shown that actually the potential for much more intense rainfall in summer in the UK is much greater than we thought from lower resolution coarse-grained models. So it's completely changing our perception of how we must adapt to changing rainfall patterns in the future with global warming. So that's where we've come. We've come all the way through that history of climate science, the fundamental physics, to being able to talk about local flooding. And that's important because I want to now sort of say, well, how does that relate to the 21st century changing landscape? And I'm going to put weather and climate risk, because that was weather that we just saw there. And this is a diagram I often use to talk about where our science fits. It's very important that when we think about weather, climate variability and change, which is what I was working on in the Met Office, that we don't forget that these things are happening within a world that is also under major pressures from urbanization, population growth, and limited natural resources, of particularly water. Water will arguably become the most precious resource on the planet, I think, in the next few decades. So we have to look at it in that context. And therefore, it's no good to say, well, okay, we've had climate change in the past, or we've had these things in the past, and it was all fine. The point is that the world is not the same as it was in the past. There are now an awful lot of us on the planet, and we live in big cities, and we depend on a globally interconnected economies and supply chains. So we have to look at our science in that context. And these things in this middle circle essentially influence the securities on which we rely for our health and well-being. And again, what's really important here is that we don't look at each of these in isolation. You can't look at food security without looking at water security and so on. They're all interrelated. So we have to think now of our science in place within this broader context of the things that we rely on for our health and well-being and for the sustainability of the planet. And therefore, you know, my feeling was that 2015 was really quite a landmark year in lots of ways. We had Paris, first time governments had accepted the evidence for climate change and agreed to do something about it. We had the Sendai Agreement on disaster risk reduction, and we had the Sustainable Development Goals. And all of those depend on a strong basis in weather and climate science. And so, you know, this is sort of some grand words, but actually this is very real, and we see this happening now, not in the future with climate change. And interestingly, if we wanted to argue the case for our science, this is from the World Economic Forum last year, looking at the likelihood and impact of the global risks and what's at the top. Everything to do with extreme weather events, natural disasters, failure of climate change mitigation and adaptation, are regarded as the most critical, the top risks, and some down here as well too, but actually I think that's very striking. So we have to advance our science, and it's fortunate that I think we do have some new tools in the toolbox. These are from my time as chief scientist, but these are important. This concept now that we forecast across timescales seamlessly, from near-term weather to what we call the extended range, to the monthly to decadal. Actually, this timescale, the next year or the next 10, 20 years, is actually where a lot of people are going to make their decisions. And then we've got long-term climate change. But the idea here is that the same science, the same modeling techniques go through all these timescales. You add different things out here to do with the Earth system that you don't need back here, but the fundamental atmosphere-ocean science is the same. And likewise, we've seen this just now, this concept of seamless prediction across space scales from the global models that we run in climate and in weather forecasting to get what we call the synoptic drivers of local weather, through to what I was just showing you, the regional predictions at 1 kilometre to give you the local meteorology, and then feeding that into all sorts of impact systems to get both the probability of local hazards to give you impact scenarios and narratives. This is flood risk in this particular case. But this is the way the science has developed, so we're actually in a place where I think we can do some useful things. So just very quickly, I wanted to just give you a couple of examples. This is the UK in early part of 2014 and in December 2015, terrible flooding. And I was very much at the sharp end of some of this, being the chief scientist. And of course, what you get from the minister is, well, first of all, is this climate change? Well, actually, when you look at the rainfall and river records for the UK for the last 100 years, you can't say. We have a hugely variable climate. It was very hard to say it's climate change. And then the minister went on to ask me, particularly after this event, he said, how much rain could we get? Could we get 3 times the amount? What is the plausible worst case for UK flooding in the next 10 years? And you go, how do I answer that? And he wants the answer in 6 weeks. So when you work in policy-related science, you have to move fast. So these were really, really difficult questions. They look simple. He thought they were simple. They're very difficult to answer. So what did we do? Well, actually, I'm going to take you back to another bit of fundamental science. And this is Ed Lorenz and his famous quote, "One flap of a seagull's wings may forever change the course of the weather." And this has been the fundamental part of why we do ensemble prediction. We never make one forecast anymore. We make 50 or whatever. Because we know that chaos theory tells you that small perturbations grow and gradually change the sequence of the weather. Sometimes in a very constrained way, and sometimes in a very broad way. But you can also argue, of course, that if you take that concept, there are lots of worlds that might have been during the period in which we've observed the planet, but we haven't observed them because we didn't get the flap of the seagull's wings in one place or another. So you have to remember that observations is only one plausible realization of what the world's weather could have done, say in the last 30 years. And when you accept that, you then say, well, actually, could I use then multiple realizations of the weather from simulation as paths that the world's weather could have taken, but we happened not to observe? So this idea that there might be black swans out there, very extreme events, that just could have happened if the weather had set up in a different way because of chaos theory. If we chopped down a different bit of forest or done something different with our cities. That's the flap of the seagull's wings. So what we were able to do was actually to take, we had 1,400 years of simulated weather from 1980 to 2010 because of part of another project. So we had 1,400 simulated winters that were all perfectly plausible versus 35 observed winters. So it was from 1980 to 2015. And then you can say, well, here, this is for southeast England. These are the range of the observed monthly rainfalls during the winter. And we've only got 35 samples. And you can sort of plot a distribution, but quite frankly, the tails are not well populated. Here's the model simulations, and they were quite plausible simulations. The model was quite good, actually, surprisingly good. It's quite a high-resolution model. And we've put in red the ones that lie outside anything that's been observed, right? And so you've actually filled up the distribution function much more effectively, both at the dry end, but here we're interested in the wet end. And you've got quite a large number of events, the wetter than anything you've observed in the current climate, just from natural variability. There's January 2014, the Thames flooding, which was an extreme outlier compared with the previous years. But actually, if we'd had this information, we might not have been so surprised that it happened. And there's one that's actually worse than that. So then you can go away and answer the question that the minister wanted, which, well, what's the chance? And he wanted a 1 in 100 year chance. Well, I don't know how you do a 1 in 100 year event when you've got about 50 years maximum of data, not sure. But actually, you can do the 1% risk. So here we've got, this is the percentage increase in rainfall above the maximum that we've currently observed. And this is the chance of the event. So, and here's the probability taken from the simulations. And we can say that actually at the 1% level, there's a chance of having between 25 and 30% more rainfall, 20 to 30% more rainfall. It's not 0 and it's not 100. It's actually quite well constrained. And every year you might expect there's a reasonable chance that you'll break a new record. It's between 5 and 10%. If we had done that with only 35 years of data, which is what we've got for the observations for the current climate with CO2 forcing, then you can see how unconstrained the tails of the distribution are. You can't really talk about the risk of a 1% event. It's anything across here. And this is a big problem. For most of the things to do with the insurance industry and many of the infrastructure investments, we're having to work at 1 in 100 year events. The insurance industry works entirely on the tails of distributions, which are not well characterized from observations. So there's a real role here now for simulation to provide synthetic event sets that can allow us to populate or fatten up the tail, as the insurance industry says, to give better estimates of risks of extremes. So this is a very exciting development. And I think, we're just beginning to explore this, applying it to all sorts of aspects of the world's climate, from heat waves in China to heavy rain in the UK and elsewhere. So very exciting. That's only one bit of the story, though, because actually what we really want to know is, at the regional, local level, what are we going to do? This is the Thames Barrier. Is it good out to 2100 is a good question. In 2013-14, the Thames Barrier was closed more than it was open. It was closed most of the winter because of the extreme rainfall and extreme storms that we had. So it was a bit of a wake-up call, is how well do we know these things? And this is our #1 risk in the UK, is East Coast storm surge. But how can you characterize that risk? Well, we started a really groundbreaking project while I was at the Met Office having experienced those extreme events, thinking about, well, how are we going to get a better understanding of the fully coupled near-surface environment? So the UK, the Thames, is exposed to river flooding, storm surge, tides, all those things. So this was a project we started, an integrated coupled predictions for the UK at the convective scale. Relevance to people, ecosystems and infrastructures. This is what people really want to know about if we're going to manage our risks. So this is what we've built in the last 3 or 4 years, published in Geophysical Model Development by Hugh Lewis, who worked very closely with me when I was chief scientist. And we've built this 1.5 kilometre model of the atmosphere, the land, the waves, and the coastal shelf sea. I think it's a first. It's very, very innovative. This is not going to be operational, I don't think, for another 5 to 10 years, but very exciting. And just a little snippet of what we get out. Well, this is sea surface height. Many of you won't know, but the UK experiences incredibly high tides. This is the tidal range in here in meters, from more than 8 metre tidal range in many parts of the country. This is the tide propagating around the shelf sea of around the UK. And so tides are an integral part of our environment, not necessarily others. The tides, here we are from the shelf sea model. This is surface currents, and we can see, we speeded up a bit, the tides also drive very, very strong surface currents around the coast. And some very interesting coastal currents you can see when you're down at 1.5 kilometres, and the interaction with the shelf here is fascinating. And there's been a lot of analysis of this. We've added waves, and here's a couple of examples of extreme wave height. One up on the east coast here, which is in the North Sea. This is an uncoupled simulation of the wave height. This is the coupled in red and the observations in black. So a fully coupled atmosphere, ocean, wave, tide model gives you estimates that are at least 0.5 metre bigger than you would get from an uncoupled model. And 0.5 metre, when you're thinking about sea defences, is quite significant. This is actually Hinkley Point, where we're building a nuclear power station. And this was another example. I was asked what a 1 in 10,000 year event was for Hinkley Point when I was chief scientist. That was interesting. Didn't know how to do that, really. But here's Hinkley Point, very, very different wave spectrum. But again, if you're concerned about extreme wave heights, really it's only the coupled system that gets anywhere near the observations. Here's the work we've done. We have a very complex river system in the UK. This is our interactive now coupled hydrology and river flows. This is part of developing a much better estimate of river flooding and how we manage rivers from this very high resolution model. Some very exciting stuff. We have a lot more to do, including also the coastal biology and the health of the coast. And we've started to work with other countries, particularly Singapore, where the local environment is also very complex. So I think this is a really exciting breakthrough. So if we think about what the 21st century is going to require of us, then I think, thinking of environmental risk is going to pose major challenges to society. The science of weather and climate lies at the core of managing many of these risks, whether it's through simulated event sets and narratives, the sorts of things I've given you a sense of. We have to get a better understanding of the coupled local environment in which we live, and that, I think, is the next step for a lot of our science, is getting down to that local environment level. But I just wanted to end up, because I'm here at JPL and it's NASA, I wanted to end up by just saying a little bit about, leave the last word almost to Piers Sellers, because he was very, I think, inspirational. Many of us knew him in his early years as a land surface modeler, and he went on to be, of course, an astronaut, and here he is in the space shuttle. And he died, as many of you will know, of pancreatic cancer about 2 years ago. And the year before, he wrote a really, I think, fantastic piece in the New York Times. And this is what he said when we think about the challenges we face for the future. He said, "New technologies have a way of bettering our lives in ways we cannot anticipate. There is no convincing demonstrated reason to believe that our evolving future will be worse than our present, assuming careful management of the challenges and risks. History is replete with examples of us humans getting out of tight spots. The winners tended to be realistic, pragmatic, and flexible. The losers were often in denial of the threat." I met quite a lot of those losers when I was chief scientist. People who, senior people who denied that climate change existed and that it was all a hoax. They were in denial of the threat. He then goes on to say, "As an astronaut, I spacewalked 220 miles above the Earth. Floating alongside the International Space Station, I watched hurricanes cartwheel across the oceans. The Amazon snake its way to the sea through a brilliant green carpet of forest, and gigantic nighttime thunderstorms flash and flare for hundreds of miles along the equator. From this God's eye view, I saw how fragile and infinitely precious the Earth is. I'm hopeful for its future." Wonderful piece by him. There's so much more in that to read, actually. And so I think, you know, coming back to the beginning, climate science is about helping us to live safely and sustainably on our planet. And I just want to end with a bit of what might look like frivolity, but it's not. I think it's quite a profound message. This is Linus from Peanuts, and he's out there and he's on the beach. And he's building this fantastically ornate sandcastle. And I often think about that when I see climate impact assessments and the sort of information that we sometimes give out to ministers. We've built this fantastically complicated assessment with social scientists and engineers and so forth. And it looks a bit like that. We'll all have seen them. But the problem is, as he finds out, is that the rain comes down. And he says at the end, "There's a lesson to be learned here somewhere, but I don't know what it is." And those of you who remember going to Sunday school might well remember what the lesson is, of course, is that a foolish man built his house on sand. The rain came down, the streams rose, and the winds blew and beat against that house, and it fell with a great crash. And of course, what did the wise man do? The wise man built his house on the rock. The rain came down, the streams rose, and the winds blew and beat against the house, yet it did not fall, because it had its foundation on the rock. And what's really important here, and one of the things that concerned me when I was chief scientist, is that whatever advice we give to people who have to make decisions and set policies, that we need to ensure that the bedrock of science is there. And this is a really important message. Climate and weather science is not done. It's a long way from being done. And we have to be aware, as I often was in talking to ministers in government, to be really honest with them and say, I can't answer that question because the science isn't good enough yet. As we move into this world where we're going to be asked, challenged time and time again about environmental risk, we have to be absolutely honest and ensure that we get the investment in the bedrock science. The sorts of stuff that you're doing here with Earth observations, the sort of stuff that my folk at the Met Office are doing with building better and better models. We have a long way to go if we're going to provide the quality of information that we need to deal with 21st century challenges. So that may seem like a bit of frivolity, but the message, I think, has to be very clear. So thank you very much for listening. I've run on far too long.
We'll do questions for like 5 minutes, maybe.
No time for questions.
No time for questions. Yes. Yeah, I see a hand waving. We're going to take some questions for about 5 minutes. I know it's lunchtime. We're going to run it over into about 5 minutes or so for questions. Wait for the mic, because this has been recorded.
Hi. I wonder if you have an opinion on what I perceive to be the fundamental problem which you're getting at here, which is, my brother was in the Australian civil service and eventually became fairly high up, as in second to minister. And his perception of the problem goes something like this. Technical person says to minister, we have a perception of a problem with a certain amount of uncertainty.
Yes.
And the minister says, you want me to commit how much money to your confidence level?
Yes.
Go away.
Yes.
Is there an answer to that?
Yes. I mean, this was obviously, this is at the root of a lot of the work that we were doing in the Met Office. And it's to some degree, it's about language that we use. So we shouldn't use the word uncertainty, because that's not what this is. I mean, chaos theory is not uncertainty. It's about probabilities and confidence. So that was the first thing. And then you have to sort of actually start to work with these people and look at the cost-benefit ratios. Where's their decision point? So that it's not just there's an uncertainty. Where is it that it's important for you to make a decision, depending on how much it costs? And actually, it's a lot about just educating people about how we produce these probabilities and how they should use them. After all, every decision we make in life is based on, we make a risk assessment. You may not realize it, but we all make risk assessments, virtually everything we do. But it's about how you've got to have that dialogue with the minister. And actually, this one was, the example I showed of flooding was a very, very interesting discussion. I actually sat with the minister. He wanted to know how climate models worked. Once he understood all that, and he understood what we were doing and how we were couching it, he could actually describe it. Not all ministers are as good at this. I think we can't get around this, that we have to work with probabilities, but I would like to think that we can use better words, positive words like confidence. There are messages where you can say, I'm absolutely confident that it will be like this. And we can use narratives. I mean, I didn't talk about that too much, but actually very keen on taking some of the tails of the distribution and building a narrative from what the simulation is telling us about how the weather evolved. And therefore, you can run almost like a test case of what your response would be to it within that narrative. I'm not sure I've really answered your question very well, but I mean, this is the fundamental thing that we have to, in all walks of life, as we go through, we're going to have to deal with probabilities and risk. And it's about having the right dialogue at the right level. And I think the main thing for me when I was chief scientist was to be absolutely clear that anything I said, whether it was a probability or whatever, I could justify the scientific basis for. And so I think this is still for me the key thing, that we have to be sure that we can go back to the science and say, I can or I can't answer that question yet, but not try and give a half-baked answer on probabilities that you don't believe in, right?
I can give you a more difficult question. So your tied climate change to weather extreme events, which are local in space and short in time.
Yes.
What about structural changes like abrupt changes which happened in the past. I know, like Younger Dryas and so on.
Yes.
What about this?
Well, they would have been the same sort of thing. I mean, the Younger Dryas was driven by a completely different process. And we would... Pardon?
It was global, structural.
That's right. But the point here is that what we feel as individuals is not the global change, but the change where we live and the weather that we experience. That's absolutely true. The Younger Dryas, yes, was a global change. It was a massive change. And everybody will feel it, but actually at the place where there was, at the individual or the country level, it's about the weather. It's not about the global mean change. It's how that manifests itself in the weather that you experience.
If you work for the government.
Yes.
We'll take two more. One from Dwayne. I think there's one up the top there.
Relevant, for example, the sea ice in the Arctic going away. That's not a weather extreme. It's more along the lines of what he's talking about, for example. Right?
Yes, I mean that is a good example because, but there, who's going to be impacted? Well, it's probably going to be the Arctic, the Inuits, and the Arctic ecosystems, and maybe the loss of Arctic sea ice could have an impact on UK weather, for example. So that's an example of a big change. But actually, most of the changes that we're going to see are going to be along the lines of more extremes, whether we want to call them weather extremes or extremes of climate variability.
One last question and we break for lunch. Okay.
I'm just curious, can we engineer favorable scenarios by having seagulls flap their wings?
What did she say?
She said, can we engineer favourable scenarios by more seagulls flapping their wings?
Probably not. Chaotic system doesn't quite work like that, unfortunately.
You've probably got equal chance of being unfavourable as favourable.
Precisely. Yes.
Okay, so I think we'll thank Julia again for a wonderful talk. And we have lunch somewhere. One's organised lunch. I think it's somewhere. I'm not sure.
Is that
Thank you
right?
very much. Yeah, it was fantastic. Thank you.